So our next lecture is relative motion. This covers section 1.6 in your textbook. And a good situation that describes relative motion would be that of a person in an airplane. And if you've flown in an airplane before, you might have noticed that when you look outside the window of an airplane, it appears as if the clouds are moving very fast. And when you look at the motion inside the airplane, it's as if the plane itself is stationary and the clouds are just moving around it. But if you're an observer on the ground and you look at an airplane, you see the airplane moving with respect to the ground. But the clouds themselves, you see them moving as well. They'll be moving with respect to the wind. So the wind is independent of the movement of the airplane. The movement of the clouds is independent of the movement of the airplane. That would be your perspective as an observer on the ground. Now this is an example of relative motion. The passengers in the airplane are in one frame of reference, and you being an observer on the ground are in another frame of reference. Now when we find the velocity of an object relative to a specific frame of reference, that's called the relative velocity. You'll find that for some problems that involve multiple types of motion in different frames of references, that determining the relative velocity often simplifies solving these types of problems. Now, I'd like you to copy down the definition of relative velocity. You may want to pause in order to do that now. So to analyze relative velocity in more than one frame of reference, we use the symbol for relative velocity with two subscripts in capital letters. So what you see here is an example of showing the velocity of a canoe relative to water. So we show V with an arrow above to recognize that this is the velocity vector. And we write C, which is canoe, and then we write W, which is water. This is read as the velocity of a canoe relative to the water. So here's another example. This one involves a plane moving relative to the Earth, and the plane moving relative to the air, and the air moving relative to the Earth. So here we have an airplane. It's traveling at 490 kilometers per hour west relative to the Earth's frame of reference. So its VPE, which is its velocity of the plane relative to the Earth, is 490 kilometers per hour west. So let's look at the wind. The wind is moving with respect to the Earth as well. Here we're going to label the wind as A, or air as A, and the plane is labeled as P. So VPA is the velocity of the plane relative to the air, and that is also sometimes called the airspeed of an airplane. And then lastly, we have the velocity of the air relative to the Earth, and that would be VAE. So velocity of A, which is the air, relative to E, which is the Earth. And we call that wind speed. And going back to the velocity of the plane, the VPE, that's sometimes called the ground speed as well. These are terms that are used when talking about relative velocities of any object that's traveling with respect to the Earth while it's also experiencing wind as well. So the equation VPE equals VPA plus VAE, in the situation that we had above, we know that the plane is moving at 430 kilometers per hour east, and the air's velocity relative to the ground is 90 kilometers per hour east. So if we want to find out what the plane's ground speed is, we add the air speed plus the wind speed. So 430 plus 90 gives us 520 kilometers per hour east. Now what you may have noticed in terms of how those variables work, or those subscripts work in the variables, that when we add a variable or a relative velocity variable to another relative velocity variable, if the last subscript is added to another relative velocity vector, and the first subscript is equal to the last subscript of the other, then our resultant becomes the relative velocity of the outside terms. So this example, if you look at this picture here, we have VPE equals VPA plus VAE. The A is on the inside, and when we add VPA plus VAE, what essentially happens is that A gets covered by the calculation between VPE. So our VPE is a sum of VPA plus VAE. This works with any relative velocity. So here's some random letters here. We have VDG. That would be equal to VDE plus VEF plus VFG. So the E is on the inside, the F is on the inside. Our resultant velocity vector becomes VDG, which is the two outside terms. Here's a sample of a problem you might get when you're solving a relative velocity assignment. So here we have a cruise ship. It's moving with a velocity of 2.8 meters per second forward relative to the water. And we have some tourists that are walking on the deck with a velocity of 1.1 meters per second relative to the deck. So we're asked to determine the velocity of the tourists relative to the water. And we're asked to do that when they are walking toward the bow of the ship. The bow is the front of the ship. So our velocity of the tourists relative to the water can be found by finding the velocity, the sum of the velocity of the tourists relative to the ship plus the velocity of the ship relative to the water. Our VTS is 1.1 meters per second forward because they're walking toward the front of the ship. The ship is also moving in the forward direction, so that's 2.8 meters per second forward. So 1.1 plus 2.8 gets us to 3.9 meters per second forward. This is the velocity of the tourists relative to the water. So while they're walking 1.1 meters per second on the ship, they're also moving with the ship at 2.8 meters per second. So their total velocity is 3.8 meters per second forward. So let's say those tourists are now walking to the stern of the ship. So this would be it would be the same calculation. It would be VTW equals VTS plus VSW. But in this case, our velocity of the tourists is now going to be a negative 1.1. So they're going back because they're going backwards. So it's 2.8 forward plus negative 1.1 forward. So when we subtract those two, we get 1.7 meters per second forward. Now it gets a bit more complicated if they're moving to the right side of the ship, or starboard. In this case, we now have a vector sum, and that's 2.8 meters per second forward plus 1.1 meters per second to the right. And I'm just going to take a quick cut of this video, and we'll switch to the paper, and I'll show you how to solve this part of the problem. So remember, for this problem we had VTW equals VTS plus VSW. That was the velocity of the tourists relative to the water is equal to the velocity of the tourists relative to the ship plus the velocity of the ship relative to the water. And what we knew was that our velocity of the tourists relative to the ship was 1.1, oops, not 1.8, 1.1, and they were going to the right. So we're going to put our direction bracket here and put right. And that is being added to 2.8 forward. So when I'm doing a vector addition, I can't add anything here that is in a different direction. So I can't add a right to an F. Even if it's a down and a forward, or a backwards and a forwards, I should really write them in the same, and then in order to do that I can just flip them. But there's no way I can turn this right into a forward, or I can turn this right into a backward. So what happens in this case, because one of these is entirely in the x, this is our x, that's our horizontal, and one is entirely in the y, our vertical, what we'll do is we're going to turn this into a vector addition problem. And how this looks graphically, we have 1.1 to the right, meters per second to the right, and then I travel 2.8 meters per second up. So I don't travel that, but that's my velocity. My resultant here, my VTW, is that resultant, and I will need to determine what the angle is of that as well. So what you would notice here, if these are cardinal directions. This is going directly to the right, this is going directly up. So because these are cardinal directions, that makes this a right angle. And this being a right angle triangle, it's rather easy to solve VTW. We can use the Pythagorean theorem. VTW equals the square root of 1.1 squared plus 2.8 squared. And after I solve that, I'm going to get something very similar to 3.0. And that is, that would be my meters per second. That's my direction. However, what I need to do now is I need to find out, that's my magnitude. I need to find out my direction. In order to find out my direction, I need to find out this angle. And that angle here, if I look at this triangle here, this would be an opposite over adjacent. So this could be an inverse tangent of 2.8 over 1.1. And when I solve for that and I round to the nearest degree, I'll get 21 degrees. So, looking at this, I'll have to report my final answer. So I will say my VTW, I'm running out of space here, is 3.0 meters per second. And that would be, I would like to write it like this: right 21 degrees forward. And that would be my final answer. I prefer that when you get a final solution, you put a box around it. That'll show me when you're doing your work that that is your answer. Now, because we do a lot of vector addition in this course, what I recommend you do is you can go, instead of drawing the triangle, you can go straight to this step. So I'll redo this problem really quickly, and I will model how you can solve this. After this point, you could just simply go into the square root of 1.1 plus 2.8. These are both squared. This is vector addition. So if we have cardinal directions, we go straight into vector addition like this. We'll end up with 3.0, and then you'll need to do a quick little side calculation. The inverse tangent of 1.1 over 2.8. That equals 21 degrees. And going back here, you can write that in. It is right 21 degrees forward. And I will box that solution. So here's another problem. We have a canoeist who can travel at 4.5 meters per second in still water, and they're crossing a river that's flowing with a velocity of 3.2 meters per second to the east. The river is 220 meters wide. So if the canoe is aimed northward, what is the velocity of the canoe relative to the shore? So in order to solve this, we need to find the velocity of the canoe relative to the shore. And we know the velocity of the canoe relative to the water. That's the 4.5 that the canoeist is capable of traveling. We know the velocity of the water relative to the shore as well. and that would be 3.2. Excuse me. So this becomes 4.5 meters per second. This would be going northward, plus 3.2 eastward. So what I can do here is I can go straight into my square root of 4.5 squared plus 3.2 squared. Because this is north, that is east, there's no way I can write this in such a way that they're both in the same cardinal direction. So when I find the square root of 4.5 squared plus 3.2 squared, and I round for 1 decimal point, or rather for significant digits, I end up with 5.5 meters per second. And I'll do a quick side calculation. The inverse tangent of the lower value, 3.2, over the higher value, 4.5, and after rounding gets me to 35 degrees. So this tells me, this 35 degrees is my direction. This tells me the direction I'm traveling, going towards the east first, then I make this degree turn towards the north. So once I have that, I write down east, 35 degrees, north. And I box this solution. I prefer when you answer these questions as well that your degree measure here for your direction is always 45 degrees or less. So if you took this as 4.5 over 3.2, you'd end up with a larger value here. If that happens, just do 90, subtract that to find the complement, or redo it where you do inverse tan of the lower number over the larger number. And make sure these directions are correct. It's east, 35 degrees north. Another part of this question, it says, how long does it take the canoe to cross the river? So if we are going to try to solve this, we now know how long the we know the resultant velocity of the canoe. But the interesting thing is that in order to determine how long it takes to cross the river, we're only interested in that north direction that it's traveling across the river. We're not interested in this direction here. We're only looking at that north component. So you could break this up into the components, which would be 5.5, and then you would do the sine of 35 degrees to determine what the north component is, but we know it's going to be 4.5. So our velocity in this case is 4.5 meters per second. And we know our distance to be traveled, which in the question said it was 220 meters. So velocity equals d over t, which means that t equals d over v. That's 220 over 4.5. And after rounding for significant digits, we end up with 49 seconds. And I will box that because that's a solution. How far downstream does the canoe land is the next question. So as we're traveling along, for this 49 seconds, we crossed the river, but we were also traveling 3.2 to the east. So to determine how far down it travels, we need to rearrange this equation, d equals v times t, where our v is 3.2, our t is 49, 160 meters, and this would be to the east. So one last question I'll show you here. It says an airplane flies due north over Sudbury with a velocity relative to the air of 235 kilometers per hour and with a wind velocity of 65 kilometers per hour northeast. Calculate the speed and the direction of the airplane. Now in this case, what we're going to do, it's the same kind of idea. We're going to, just let me switch over to the camera. We're going to look at our vectors, our relative velocity vectors. We're looking for the VPE, the velocity of the plane relative to the Earth. And we're trying to determine that with the velocity of the plane relative to the air plus the velocity of the air relative to the Earth. But our velocity of our plane relative to the air is 235 kilometers per hour, and that's going north. And the velocity of the air relative to the Earth is 65 northeast. So in order to solve this, we need to break this up into its components. So to do that on the side, essentially what this looks like is we have a vector that has a magnitude of 65 kilometers per hour. It has an angle of 45 degrees. If I want to span this 65 kilometers per hour onto the x-axis, I need to find the 65 cosine of 45. And if I want to span that along the y-axis, I need to find 65 sine of 45. Now in this case, it's going to be just exactly the same, but I will do those quick side calculations. So this 65 northeast can be broken up into 65 cosine of 45 degrees, and that would determine my east direction, plus 65 sine of 45 degrees, which would determine my north direction. So in both of those cases, what I end up with is my 65 northeast becomes, and I'll keep an extra decimal point here, 45.96 north plus 45.96 east. So putting that back into this equation here, 235 plus 65 east, so that's 235 north plus 45.96 north plus 45.96 east. So that becomes 280.96 north plus 45.96 east. And I have to vector add those two. That works out to, just give me a quick second here while I that works out to 284.69, and that is going to be in kilometers per hour. And I will have to determine what the angle is, so I'm just going to do the quick side calculation. Inverse tangent of 45.96 over 280.96. It gets me to 9.29 degrees, which I can round to 9.3 degrees. Actually, before I put that in, I'm going to round this as well. So if I look back at my original question, I had three significant digits. I had 235 and I had 65.0. That decimal 0 implies that the 0 is a significant digit as well. It's a measured value. So that means my answer here should have three significant digits. So I'll write it as 285 kilometers per hour at an angle of, the 45 is east, 9.3 degrees to the north. So that ends that lecture. I recommend you do the homework for that, and if you have any questions, feel free to ask them on the discussion board in the course website, or you can ask them on this YouTube lecture.